Hello everyone. So today we're going to discuss the topic of cylinders. As you can see, I have noted down here that there are the different sizes of cylinders. The sizes are from the alphabet letter A to J. A being the smallest cylinder and J being the largest cylinder. And the most commonly used cylinders on the anesthesia workstation are size, the type C, D, and E, of which E is the most commonly used, and the volume of the type E cylinder is 5 liters. Okay. These cylinders are filled up to a certain service pressure. So, what is the service pressure? It is the maximum pressure to which you can fill up this cylinder at 70 degrees Fahrenheit. Okay, you cannot exceed this filling pressure, this service pressure, except for oxygen cylinder. So, except for oxygen cylinder, helium, heliox, and carbon dioxide and oxygen cylinder. So, now mainly of concern is this O2 cylinder because we're using O2 cylinder in current practice, right? In our daily use. So oxygen cylinder, additional 10% pressure can be filled into the cylinder. So if you can see, the oxygen cylinder is filled up to 1900 psi, okay, but 10% more can be filled in it. So sometimes it is filled up to 2200 psi. So what is this psi? Let's go through some of the pressure units. So what are the pressure units which are used to measure the pressure of the cylinder? So we have PSI, which is a pounds per square inch. Then you have the PSIG, which is a pounds per square inch gauge, which is the measured pressure subtracted the atmospheric pressure. Then you have the PSIA, which is pounds per square inch absolute, which is the PSIG plus atmospheric pressure, and the other unit is kilopascal. Okay. Now let's see the contents of the cylinder, because the cylinder contents can be in the liquid form, can be in the gaseous form, or can be in the mixed form. So let's see which gas exists in what state in the cylinder. So here we can see that oxygen, nitrogen, air, and helium are existing in the compressed gas form in the cylinder, whereas nitrous oxide, carbon dioxide, and cyclopropane exist in the liquid form in the cylinder. Now let's understand the individual parts of the cylinder. So the parts of the cylinder are what you have: the shoulder, you have the body, right? Then you have a valve. So let's understand individual parts and then we shall see the images. So here, the body of the cylinder, what is the material? The material is molybdenum steel. So this molybdenum steel is an alloy. It's an alloy of molybdenum and chromium. Molybdenum steel gives a lot of strength to the cylinder. It reduces the weight of the cylinder, and it is right now the most preferred material for making the cylinder. So when it is made of molybdenum steel, the cylinder will have a marking on it, which is 3AA. So 3AA marking cylinder is a cylinder made of molybdenum steel. Then what the other material which is available is carbon fiber, and the other material which is available is aluminium. So it can be also made of aluminium. So aluminium cylinders are used in the MRI setting. Okay. So how do you know that this cylinder is made up of aluminium? There will be a marking on the cylinder, 3AL or 3ALM, which says that the cylinder is made up of aluminium. The base of the cylinder can be flat based or it can be a concave based cylinder. Now let's understand more about the cylinder valves. Here we can see the image of different types of valves. So this is the bull nose valve. This is the flush type valve. All right. The valve material is made up of bronze or brass, and the parts of the valve. So there is something which is known as the port. So what you can see here, this where my marker is, that is the port of the valve, and it is through this port that the gases will leave the cylinder. This valve also has got a stem. So if you can see this, where the marker is, so that is the stem. So the stem is rotated to open the valve and close the valve. All right. So the stem will seal against a seat to close the valve, and the stem moves up to open the valve. Now there are two types of valves. There are important points about the valve. All right. So there are two types of valves. There is a pack type of valve, and then you have the diaphragm type of valve. So the pack type of valve, the stem is sealed with the help of Teflon material. All right. So this Teflon material will prevent less leaks. Okay. The other option is having the diaphragm type of valve, wherein there is a disc which is kept in place on the seat. Okay. And this prevents the leak of gases. So there's diaphragm type of valve and pack type of valve. Now the pack type of valve requires at least 2 to 3 rotations, all right, to open the valve. Whereas the diaphragm type of valve does not need so many rotations. Within half or a 3/4 turn, the valve will completely open. Okay, so that's the benefit of the diaphragm valve, that less rotations are needed. The second benefit is that the chances of leaks in the diaphragmatic valve are very, very low. All right, so these are the two advantages of the diaphragm valve. Now let's go through some of the pressure relief devices of the valves. Let's go through the pressure relief devices. It is a protective mechanism for the cylinder to prevent excessive pressures within the cylinder. Okay, so the first one is the ruptured disc, and the second, the fusible plug. So these two are the non-reclosing type. That is, once this disc has ruptured or once this plug has melted, you cannot close it. Okay, so the ruptured disc, when the pressure within the cylinder exceeds the service pressure of the cylinder, it is a safety mechanism. That is, this disc will rupture and vent out the excess gas. Okay. The second is the fusible plug. So this is a material that will melt. Okay. When a certain temperature is exceeded. So if the cylinder is in an environment where the temperatures are high, the pressures within the cylinder also will increase. Okay. So this is following Boyle's law. So let's just have a look at that. So Boyle's law is P1. It is P1 V1 upon T1, right? Is equal to P2 V2 upon T2. This is the Boyle's law, right? So rear pressure, temperature, and this is the volume. So pressure and temperature are directly proportional to each other, whereas pressure and volume are inversely proportional to each other. So if the temperature, ambient temperature increases, the pressure within the cylinder will also increase. This rise in pressure within the cylinder, the safety mechanism has to be in place, right? So for the fusible plug, when the rise in temperature occurs and when the yield temperature is reached, okay, this is called the yield temperature. So the yield temperature is the temperature at which this material, which is in the fusible plug, will melt. This material will melt and it will cause opening of the pressure relief device, and it will cause the release of the excess gas. So this fusible plug will only protect the cylinder in a situation where the temperature is increasing, which is causing the rise in the pressure. It's not going to protect from overfilling of the cylinder, okay, because it's purely temperature dependent. It's not going to protect from overfilling of the cylinder. Then the third is a combination of both, combination of the fusible plug and the ruptured disc. Then the fourth pressure relief device is the spring-loaded pressure relief device, wherein there is a spring-loaded valve. All right, so when the pressure exceeds, the spring opens and there is a release of the gases. All right. So this particular valve, the spring loaded pressure relief valve, can later be closed. So this is a reclosing device, whereas these two are not reclosing devices. So here we have the image of the Boden's pressure gauge. So as you can see, there is a hollow, this is the hollow metal tube which is bent, okay, like a curve. All right. And one end is sealed. So this is the sealed end and this is the open end. Okay. This open end is connected to the gas source, okay, which is this P, this is the pressure, all right. So it is exposed to the pressurized gas, okay. So the pressurized gas will enter into the tube and will make the curved tube become a little more straightened, okay. So it will cause this curved tube to become a little straightened. Now, straightening of this curved tube is going to cause this clock-like mechanism, all right. So this clockwork is going to rotate, okay. There's going to be rotation of this clockwork. This rotation of the clockwork is going to cause this pointer to move along on the pressure gauge. So that is finally this pointer is going to move on the pressure gauge. Okay. So this is the working of the Boden's pressure gauge. Let's understand the filling pressures of oxygen cylinder and the nitrous cylinder. So the cylinders which are filled with gas, they follow the gas laws, all right, because the oxygen cylinder is containing only compressed oxygen gas, okay, whereas the nitrous cylinder is filled up with liquid nitrous oxide, okay. It's got liquid nitrous oxide. So there is going to be some amount of nitrous oxide which is going to be in the gaseous form within the cylinder, as well as the remainder is going to be in the liquid form of the cylinder. So what pressure will be read on the nitrous oxide cylinder? It will be the saturated vapor pressure, okay. It will be the vapor pressure of the nitrous oxide that will be measured on the pressure gauge, okay. It will not measure the actual pressure of the nitrous oxide gas. It is going to be the vapor pressure of the nitrous oxide, whereas oxygen cylinder has got only pressurized oxygen gas, okay. So that is why it's, as the content of the oxygen cylinder decreases, it will be visualized in the form of decrease in the pressure within the cylinder, okay. So it's going to be parallel. The decrease in the oxygen content will parallel with the decrease in the pressure noted on the cylinder gauge, okay, on the cylinder. So we need to understand the gas laws, okay. So there is Boyle's law, Charles' law, and Gay-Lussac's law, and this is the combination of all the three gas laws. So P1 V1 upon T1, which is the pressure P1, the P, V, and T stands for pressure, volume, and temperature. So based on this, as you can see, pressure and volume are inversely proportional to each other. That is, if pressure increases, the volume will decrease and vice versa. So as in this law, what we can understand is that pressure is inversely related to volume. All right. Volume and temperature are directly proportional to each other. Pressure and temperature are directly proportional to each other. So this is the combined gas law, combination of the Boyle's law, Charles law, and the Gay-Lussac's law. So a full oxygen cylinder is going to be filled up to its service pressure. The service pressure of oxygen cylinder is 1900 psi. Okay, so let's see for the oxygen cylinder. The service pressure is 1900 psi. This pressure, it can be, the service pressure can also go up to 2200 psi. That is, more 10% extra can be filled into the oxygen cylinder. This is specific only to oxygen cylinder. So if it is filled 10% extra, you will get 2200 psi. Okay. Oxygen cylinder has got 660 liters of compressed oxygen within it. Okay. It's got 660 liters of compressed oxygen gas, O2, in the gaseous form within the cylinder. So how did we get this answer that there is 660 liters of compressed oxygen? So here we apply the gas law. So we apply the gas law, P1 V1 is equal to P2 V2, provided the temperature is constant. So the pressure within the cylinder, the full cylinder is 1900 psi. The volume of the type E cylinder is 5 liters. All right. The volume of the type E cylinder is 5 liters, which I had already explained to you. So, and what is the pressure? Atmospheric pressure. Atmospheric pressure. So that is 1 atm. 1 atm is equal to 14.7 psi. Okay, 14.7 psi is equal to 1 atmosphere. So we need to know how much will this type E cylinder, which is 5 liters capacity, which is pressurized up to 1900, how much oxygen gas is it going to release, is it going to provide at an atmospheric pressure? So here we want to know what is the volume. Okay, we want to know V2. So when you solve this equation, that is 1900 into 5 divided by 14.7, you will get the answer to be around 660 liters of oxygen. So that is how we know that a full oxygen cylinder, that is a full type E cylinder, which is pressurized up to 1900, which is pressurized full up to 1900, it is going to yield, it's going to yield and it's going to provide 660 liters of oxygen. Okay. So here is an application of the gas law. Now, if we know, we can again apply this similarly, this gas law. If we want to know, suppose the reading on the pressure gauge, how much is the reading? So we want to know the reading on the pressure gauge is suppose 1000 psi. Then how will we know how much oxygen is left in that cylinder? So if we know that the cylinder, this type E cylinder is reading 1000 psi, how much oxygen will it provide us at 1 atmosphere? So let's have a look at that. So here we will replace this 1900 with 1000. So now the pressure gauge is reading 1000 and this is still a type E cylinder and it's still, its capacity is 5 liters. Okay. Now we want to know how much is it going to yield at 1 atmosphere. That is how much is it's going to produce at 1 atmosphere. So when you solve this equation, okay, again, it comes 1000 over here. This is going to provide you with a value. Okay. So I've calculated it. It will provide you 340 liters of oxygen will yield out from this oxygen cylinder. Okay, so now we have learned that from the reading on the pressure gauge, we can determine how much oxygen is left in the cylinder. Okay, how long will this oxygen last us? Let's go through that as well. So now let's take another example. If the reading on the cylinder or the oxygen cylinder is 600 psi. Okay, so 600 psi is the reading on the cylinder. How much will it provide us the total volume? So let's calculate. So if you put 600 over here, okay, when you calculate, it will come to around 204 liters of oxygen. So if the cylinder has got only 600 psi pressure reading on it, it's going to provide us with 204 liters of oxygen. How long is this 204 liters of oxygen going to last us? So if this oxygen flow rate, if your flow rate is going at suppose 5 liters per minute, okay, so we have to see what is our flow rate on the flow meter. What is the flow rate? So if it is 5 liter per minute, this is an example. So how many minutes will the cylinder last us? So you have to do 204 divided by 5, which will give you what? Around 40 minutes. Okay, this will give you the answer of 40 minutes. Okay, so this cylinder will last us approximately for 40 minutes if I go at the flow rate of 5 liters per minute. So this was just an example to understand how you calculate the amount of oxygen left in the oxygen cylinder and how long will this oxygen last you. Okay. Now let's understand for nitrous cylinder. Now let's understand about the nitrous oxide cylinder. All right. So nitrous oxide cylinder, the cylinder contains liquid nitrous oxide within it. All right. So it contains the liquefied form of the gas. The pressure that will read on a full type E cylinder, that is a full type E cylinder with nitrous oxide, will read 745 psi. So this reading will be stable, it will be stagnant, it will keep showing until all the liquid within the cylinder has evaporated and there is no more liquid left within the cylinder. All right. So when there is no more liquid left in the cylinder and only the gas form, the evaporated nitrous oxide gas is present within the cylinder, that is when the pressure on the pressure gauge will start declining. That is when this pressure 745 will start declining. Until then, the pressure will keep showing 745. Okay. So this pressure will be constant until all the liquid has evaporated. A full nitrous oxide cylinder, the weight of it is 8.8 kg, all right? And an empty cylinder weight is 5.5 to 5.9 kg is the tar weight. So what is the tar weight? Tar weight is the weight of the empty cylinder. So why are we so interested in knowing the weight of the nitrous cylinder? It is because the amount of nitrous oxide that is left within the cylinder can be determined only by weighing the cylinder. So in between, if you want to know the pressure is constant, but you really don't know how much nitrous oxide is there within the cylinder, that is how much nitrous oxide will be yielded by the cylinder, you have to calculate it by weighing the cylinder. Okay. So the nitrous oxide cylinder, because the pressure is, not an indicator, the filling ratio is the indicator to which the cylinder will be filled. How much nitrous oxide should be filled in the cylinder? It is not the pressure which will determine it. It will be the filling ratio. Okay. Whereas for oxygen cylinder, which is a cylinder which is completely filled with gas, so it is the pressure gauge reading up to which, that is up to the service pressure, the filling of the oxygen cylinder will be done. But that is not the case for the nitrous cylinder. We have to look at the filling ratio. So the usual filling ratio of nitrous cylinder is 0.75 to 0.67. So in the tropical region, the filling ratio that we take is 0.67. So if we want to calculate how much nitrous oxide should be filled in the cylinder, this is the formula. So the formula's filling ratio is equal to the weight of the cylinder filled with nitrous oxide divided by the weight of the cylinder filled with water. Okay. So 1 liter water is equal to 1 kg in weight. Okay. So a 5 liter volume cylinder, will fill up 5 liter water, and 5 liter water is equal to 5 kg weight. Okay. So when you put 5 kg weight of water in a 5 liter cylinder, that is a type E cylinder, it means that when you calculate this formula, the weight of the nitrous oxide that can be filled in the cylinder is 3.35 kgs. Okay. So now we use the Avogadro's law and the Avogadro's number to calculate the amount of nitrous oxide gas that can be yielded from a cylinder. So let's understand that. Okay, so here I have explained how are we going to calculate the amount of nitrous oxide left in the nitrous oxide cylinder. So here we need to know the Avogadro's number. So what is Avogadro's number? We want to know the number of moles of nitrous oxide present in the cylinder, which is, we are following the Avogadro's number. So Avogadro's number is equal to the mass of the substance divided by the atomic mass of the substance. Remember this formula, mass of the substance divided by the atomic mass. Now 1 mole of nitrous oxide, what is 1 mole of nitrous oxide will yield 22.4 liters of nitrous oxide at standard temperature. So now since the OT temperature, that is a room temperature, is 20 degrees Celsius, it will yield 24 liters of nitrous oxide at room temperature. All right. So 1 mole of nitrous oxide will yield 24 liters of nitrous oxide at room temperature. Now what is the atomic mass of nitrous oxide? The atomic mass is 44 grams per mole. Okay. And what is the weight? Now, for example, if the weight of nitrous oxide within the cylinder is 1 kg, that is, you measure the cylinder and you minus the tar weight of the cylinder. So suppose that after subtracting, you get 1 kg weight. So that 1 kg weight, that is 1000 grams. All right. So how many moles are present in that 1000 grams of okay. So 1000 grams of nitrous oxide has how many moles of nitrous oxide? So when you divide this, okay, because you know 1 mole, the atomic mass is 44 grams per mole, right? So 1 mole of nitrous oxide weighs 44 grams. So if 1000 divided by 44 will give you this many moles, all right? So 22.7 moles are present in 1 kg nitrous oxide. So what is the volume of nitrous oxide that it will yield? The volume of nitrous oxide that it will yield is, so you will multiply the number of moles multiplied by liters. All right. So 1 mole is 24 liters at room temperature. So 1 mole. So this is the number of moles into 24 will give you 540 liters of nitrous oxide. Okay. So ultimately, what we got to know is that 1 kg weight of nitrous oxide will yield 540 liters of nitrous oxide gas. All right. So this is how you will calculate for nitrous oxide. Once the nitrous oxide has gotten exhausted, all right, all the liquid is now no longer liquid and it's only the gaseous form which is left within the cylinder. And now the pressure is going to start dropping. All right. So once the pressure starts dropping, that is when you can apply the P1. V1 is equal to P2 V2 formula, and you can calculate the amount of, that is the volume of nitrous oxide left within the cylinder. Let's understand the safety systems which are in place for the cylinder. So the very first is the pin index safety system. So by the pin index method, the incorrect attachment of the cylinder to the hanger yoke assembly is prevented. Okay, so there's a specialized hanger yoke assembly for individual cylinder, for individual gas. Okay, also there is color coding. So let's just understand it for oxygen, air, and nitrous, because these are the gases that we are routinely using on a daily basis. So for air, the pin index system is 1.5. For the oxygen, it's 2.5, and for nitrous, it is 3.5. What is the color of the cylinder? So the air cylinder is gray in color. The oxygen cylinder has got black body with white shoulders, and the nitrous cylinder is completely blue in color. Then the third safety mechanism is the Bodoc seal, which you shall see in the video. So the Bodoc seal prevents the leaking of the gases at the junction of the hanger yoke assembly. That is between the valve and the hanger yoke assembly. There is a junction at which the Bodoc seal is there, and will prevent the leaking of gases from that point. Then the other method is the cracking of cylinder. So what is cracking of cylinder? Cracking of cylinder is that before you attach the cylinder to the anesthesia machine, you have to open the cylinder slowly. Okay, open it slowly, briefly, and close it. By doing this, some amount of gases will leave through the port of the cylinder, and whatever dust or dirt is present on the port will get displaced from the port, okay, by the flow of the gas. So it is basically a clearing away the port of any dust by, that is called as cracking of the cylinder. Now, why are we doing this cracking of the cylinder? So also the cylinder, now this is related. Open the valve of the cylinder very, very slowly. Don't open it very fast. So if you open the valve very fast, large amount of gases are going through this narrow port. Okay. So large amount of gases going through that narrow port will cause rise in temperature. Okay. There'll be generation of heat in that small little space. The heat generated in that small little space, there is no loss of heat or gain of heat, because there is really no time for heat to get dissipated, because the flow of the gases is happening so fast, the temperature rise will happen so fast that there is no time for the heat to get dissipated. So here it is known as the adiabatic process. That is, adiabatic process is the process in which neither heat is gained or lost from the environment. That is the adiabatic process. So here, if you open the valve super fast, very fast, really fast flow of gases will occur. Temperature will rise in that small little space in that port, okay? And that rise in temperature, if the cracking of the cylinder has not been done, that means there would be some amount of grease or dirt in that port area. That grease or dirt in the port area can catch fire, and this fire can cause an explosion. All right. Hence, it is necessary to do cracking of the cylinder and opening of the cylinder very slowly. So these are the two safety mechanisms. All right. Then molybdenum steel. The use of molybdenum steel has made the cylinders very, very strong. So this is also a safety system. Then the gas entering the machine, okay, from the cylinder it has to go through a filter. It has to go through a one-way valve. What is this one-way valve going to do? It's going to prevent the mixture of return of the gas from the machine back into the cylinder. Also, it's going to prevent the movement of gas from another cylinder into, like, for example, that one-way valve will prevent movement of another gas into the cylinder. So if the nitrous cylinder is open, the machine there is a one-way valve which will prevent the movement of maybe air or maybe oxygen into the nitrous cylinder. The return movement of gases will not occur because of this one-way valve. Also, there's a pressure regulator which will ensure that very high pressures do not leave the cylinder, and there's a regulation of the pressure before they enter into the machine. Then the cylinder pressure gauge. So this pressure gauge, which is a Bourdon's pressure gauge, we can see on that pressure gauge what is the pressure within the cylinder. Okay. And then you have the Wood's metal. Then we have the Wood's metal. Okay. This is a material that is there between the valve, between the cylinder and the valve. Okay. So this material, that is Wood's metal, will prevent any leaks, okay, from the attachment of the valve and the cylinder, okay, that point of attachment of the valve to the cylinder, the leaks from that point will be prevented by wood's metal. And if the temperature exceeds, like, the temperature becomes very high, pressures also increase, this wood's metal will melt